Hey everybody, in this video we're going to go through some of the literature that we use for electrical nerve block modeling, and from there we'll look at how can we use the model and look at it in context of the literature. And so a great place to start, all the way back in 1952, we have the Hodgkin and Huxley paper, excellent work that models the electrical properties of the giant squid axon. And so what we have here is there's a couple parts within it. We have a sodium channel that we model as a variable resistor and some battery, which is essentially the resting potential given the ionic concentrations of sodium. We do the same thing with potassium, a variable resistor with another battery that's essentially based on the ionic concentrations and what potential that creates. And then we have the leakage current, as well as the, I think I already mentioned, the capacitor. And across that creates the voltage across the membrane. So this is only a single kind of compartment, is what we would say. In a lot of the model, we build a bunch of compartments and would link them together, so that when one starts, going up to negative 40 millivolts, and then it reaches some threshold and it begins to fire, that because it's connected to another one, usually we have some sort of resistor that connects them across. We can use that to essentially create a chain of them, which becomes a kind of a full axon. Instead of a single compartment, we can divide it up into a bunch of compartments. But so what does this give us? So this gives us a circuit within which we can look through this paper and we can look through all the differential equations that are listed out and find so here are some of the ones where we're calculating the voltages across things, as well as some of the equations for the gating variables. So we have the potassium, and I'm assuming later on we have the sodium. The point of it isn't really to understand necessarily needing exactly how these equations work, but understanding the function of the set of equations as a whole. So if I go back up and we look at the circuit again, we really just need to understand that this circuit and the equations that go with it were very important to the field, and from there we can go on to other models. So we can theoretically, and other work has been done, to use this model in electrical nerve block. Now we could do that. We'd have to set up things so that there's kind of an extracellular voltage that we would set, which is created by the electrode. But a lot of the work that we've been doing has been looking specifically at a different model, the MRG model. And so this one has a bit of a different compartmental structure. You'll notice, this one actually shows all the compartments, whereas the HH model was just a single compartment with a single sodium and potassium channel. This model has the nodes of Ranvier. Those have a fast sodium and a persistent sodium channel, as well as a potassium channel. And then we have the leakage current and the membrane capacitance of the nodes. But in this model, that's not the only compartment. We have non-nodal compartments, and those just have a resting voltage and current. So this is kind of like the leak, but a little different. And then we have a capacitance across it. So that has a membrane capacitance with some resting current, some resting voltage that we like for all the internodal segments, because those still have the ionic charges across them. And then we also have to take into account, what does the myelin have to do with this set of electronics, essentially. And the myelin just has a leak current, it has a conductance through the membrane, and that membrane also has some capacitance. And so we model that with a resistor and a capacitor. And then we've linked all these together in this kind of network structure where we connect them with some resistance, or we could say a conductance between the 2 points. And from there we could set this all up, remembering that the gates in these channels are also differential equations, and we can model all these points as a circuit and then model it across time. So this is the model, and we also have to think about what are some of the missing components of the model, because not every model's perfect and it would be computationally expensive to do a more complex model. So what are some things that are missing from this model? Well, one of the obvious ones is that it's not keeping track of where the ions are. And so what does that mean? It means it's not keeping track of where the accumulation of ions is. Theoretically, there's always sodium to pour in, there's always potassium to go out, and there's no sodium-potassium pump that's modeled here. So that's one downfall of this model. We're also not necessarily looking at the electric fields that are created in certain ways by various ions that are going on. We're also not looking at, ATP production, and this is just the axon. What about the, the soma of the cell? What about the different parts? This is also a very uniformly distributed axon. Are all of these channels equally distributed in all the nodes perfectly? There's a lot of kind of simplicities we make in the model to make it more computationally efficient, but we have to consider those when we look at using it more practically. So always be aware that every model has flaws, but it's not necessarily important that we make a perfect model. It's more important that we just understand where the flaws are and what we can account for with that. So taking this model, let's start jumping over some electrical nerve block, and we're going to look at two papers, one for direct current, one for high frequency, to kind of get a very basic understanding of what's going on with each. So this is the paper from 2004 from our group, and I think this graph really illustrates well how the blocking works with direct current. So what's happening here? We have an axon that's 50 nodes long. We're using that MRG model, and in the center we have our external electrode hooked up, and it's creating an electric field, and that electric field is creating a potential at all the nodes. And what happens there? So we turn on our DC, in this case a cathodic DC, and that creates depolarization at the central node. So if we had the electrode right here, the central node is also getting depolarized. Something interesting to note is then there's kind of a flanking nodes that then get hyperpolarized, and we call those the virtual anodes, because if you noticed, when we do anodic stimulation, it gets hyperpolarized. But okay, where does this stimulation block? And what we can see is this top line up here, this max of E, is an action potential traveling along, and then we see what the peak voltage is of that action potential. And so as it's traveling along, it goes down, and eventually it gets decreasing as we are depolarized, and by the time we get back to this hyperpolarized region, the action potential has essentially been blocked. It's no longer traversing. Interestingly, we can look at the anodic stimulation, which creates polarized flanking nodes, and we can see that the polarized flanking nodes are doing the majority of the blocking, if not all of the blocking. So we can say that the virtual cathodes are blocking, the true anode isn't. Same here, the virtual anodes aren't the true cathode. So really the importance here is the depolarization that's causing the block. And it's also important to note that in DC stimulation we have a cathode, and then we get the virtual opposing polarity of whatever it is. So that's DC stimulation if we're looking at it across the axon. What does high frequency look like? High frequency is a little different. So one thing to note, this shows all the internodal compartments as well, which is nice. But if we look at it, okay, why is it shaped like this? And we have to understand what's going on. So at the center, we have an electrode that's doing high frequency current. I believe it says, 5 kilohertz stimulation, okay? So theoretically, this is getting, a positive and then a negative, voltage set across the node. And what that really should look like is this is constantly jumping up and down a ton. And so are all of these, but slightly less. And the farther you go out, the less stimulation you're getting. And so we can say that at the center, it's bouncing around a ton. And as we go out farther, these are kind of bouncing around a little less. And then we can take this, we can average across it, and we get this profile here. Now, what's weird about this profile in comparison to a DC, or what's different about it? And what we notice that's different is we don't have those virtual opposite polarities. All of this is depolarized. There's no hyperpolarized region. And that's something interesting with high frequency. We don't get those hyperpolarized regions, and we don't really consider that portion of that we normally would have to consider in DC. Now, what you have to remember with both of these, what were the downfalls of the model to begin with? So what things are we missing out on in both of these? Well, we're missing out on what happens to the ionic accumulation when we're using either of these. Right now, it's only based on the gates opening and closing. That's the only thing in the model. So how do we account for that in analyzing the data? How do we understand this? What does the missing components, what could that possibly lead to? What does it mean when we're not accounting for ATP production or depletion? What does that mean in terms of how we can analyze it? So those are things to think about when we look at both of these. But let's go to something else. Let's look at another paper on how we can use the model to start to analyze something. So this is the 2011 paper, Dynamic Sensitivity. This was an interesting paper. This is a great way to understand how modeling really should work. You have a in vivo phenomena that you see, and then you can recreate it in the model, and then you can adjust the model to see how that affects the phenomena, to understand what mechanisms might be at play within that particular thing. So we see electrical nerve block in the rats, and so then we can adjust the sodium using various drugs, and we can adjust those sodium channels. How does that affect the block? And we can see how that affects the block in vivo. We can then see, does the model also do that? And it does. And in this case, we are changing what's the maximum conductance of the various channels. And if we look, when we change the conductance of the sodium channel, it has the most effect on the block threshold. So this is relative conductance. If we increase the conductance of the sodium channel, it decreases the block threshold and vice versa. So this is an interesting way. We can play around with the parameters in the model, and we can use that to analyze and hypothesize on mechanisms of phenomena. What are some other ways we can do it? We can obviously we can adjust the parameters. We can also just look at them, because in vivo we can't measure how open is the sodium channel at this particular node. It's not something that we can easily measure, but it's easily measurable in the model. And so if we look at this is from the 2021 paper, combining DC and kilohertz frequency. And what we can look at is okay, what are the gating variables doing? What's the voltage doing? What are the different pieces doing during whatever we're looking at? And can just looking at the variables and analyzing them, what are their trajectories? If you start including other things in the model, how do all of those pieces of the model play together? Can you use that as an explanation for whatever the phenomena is? So in this case, you can look at the M and H gates, the two gates of the fast sodium channel. We can look at them and say, okay, well, when we have two columns here. One of them, we precede kilohertz frequency stimulation with DC, and one of them we don't. So it's just kilohertz frequency. This one's DC and then kilohertz frequency. And we can see that without DC, the M and H gates have to kind of travel around, and they swirl around into their cycles to where they're going to go for the stable state for kilohertz frequency. But if we proceed it with DC, we can start in a different point of this state space. So we can start with different M and H values when we turn on the high frequency. And that's one reason we could hypothesize that the DC puts it into a state similar to the kilohertz frequency, and because of that, it reduces the onset. At least that's what this particular paper was about. Could we look at other things? This doesn't show the potassium channel. Could we look at also how the voltage, it creates profiles. One thing is that if we did internal stimulation, that wouldn't create flanking nodes either. Does that help? And there's a lot of other things we could play around with in that aspect. And so sometimes just looking at the values themselves and analyzing them that way can also give you some mechanistic views of what's going on. So hopefully this was a kind of quick dive into some of the literature, some of the basics of understanding electrical nerve block in the model, and how we can use the model to better understand what's going on in our experiments. So hopefully this was helpful, and we'll see you in the next one.